All right, let's dive in. Today we're taking a look at a really powerful tool from the Pascal GPT data engine called the TDataframe. Now this was built to bring the kind of easy data science you see elsewhere right into Delphi, but with the raw, native speed that Pascal is known for. So let's see how it actually works.
So what are we really looking at here? To be clear, this is not just another data grid. This is a high-performance columnar data store that's been engineered from the ground up for the tough demands of machine learning and heavy-duty data processing, all right inside your Delphi apps.
And this really gets to the heart of the matter. If you've ever messed around with pandas in Python, you know just how flexible and powerful a data frame can be, right? But you've probably also hit that performance wall. Well, TDataframe is designed to give you the best of both worlds, a familiar, easy-to-use API that runs on ridiculously fast, multi-threaded, compiled Pascal.
Okay, so let's actually take a walk through the Dataframe demo code to see how this thing works in practice. And our first stop, the first stop in any data pipeline, is just getting the data into the frame.
It all kicks off with this single line of code. Now, don't let that simplicity fool you. Behind the scenes, that one command fires up a highly optimized, multi-threaded parser. It's basically using a map-reduce approach. It breaks the file into chunks, lets all your CPU cores chew on those chunks in parallel, and then stitches the results back together, all to load our entire 100,000-row sample dataset at lightning speed.
And here's the really cool part. Especially for you Delphi veterans, it's not just for CSVs. As the demo shows, it can load directly from any T dataset. That means you can hook it up to a FireDAC TFD mem table, point it at a complex SQL query, and it just works. It automatically figures out the data types and pre-allocates all the memory for you. It's designed to fit right into the database apps you're already building.
And the proof is in the pudding, right? The demo stopwatch doesn't lie. 100,000 rows, 5 columns, loaded and ready to go in just over 100 milliseconds. That is the power of a native, multi-threaded approach. There's no interpreter overhead, just pure compiled speed. Okay, so we've got the data loaded. What's next? Well, you can't work with what you don't understand. So for our next stop, let's see how we can actually peek inside and get a feel for what our dataset looks like.
And hey, if you're coming from the Python world, this is going to look super familiar. We've got a head method. The demo calls this to give us a quick glance at the first 5 rows. It's an absolutely essential first step just to make sure everything loaded correctly and looks the way you expect it to. Simple, familiar, and so useful.
But just seeing the first few rows isn't enough, right? We need the big picture. And for that, the demo uses another one-liner that is just incredibly powerful: describe. With this one command, we're telling the data frame, go figure out all the important stats for every numeric column you have. And boom, here's what you get back. For every feature, you see the count, the average, the standard deviation, the min, and the max. This is so crucial for spotting weird outliers or just getting a handle on your data's distribution. The magic behind why it's so fast is a clever thing called Welford's algorithm. Basically, it calculates all of these stats in one single pass over the data, so it doesn't have to keep rereading it from memory.
You know, in a perfect world, our data would arrive perfectly clean and ready for analysis. But we don't live in that world, do we? Raw data is almost always messy. So our third stop is all about the pre-processing pipeline, a critical step that we can see laid out right in the demo code.
The demo shows us a pretty standard workflow. First, we label and code the category column. You got to turn text like cat_1 into numbers, because machine learning models eat numbers, not words. Then, we normalize a feature to get all the values on a similar scale, which is super important for a lot of algorithms. And finally, we shuffle the data to make sure the model doesn't accidentally learn something from the order of the rows.
But here's the really slick part: how it shuffles. Instead of physically copying and moving all that data around in your computer's memory, which is slow, it just shuffles a tiny list of pointers to the rows. This is what's known as a zero-copy operation. It's incredibly fast and memory efficient, and it's a core design principle you'll see all over this framework.
All right, so we've loaded our data, we've explored it, and we've cleaned it up. Now for the final and most critical step: feeding that data to the model. In the world of deep learning, this means getting it to the GPU, which, let's be honest, can often be a major performance bottleneck. Let's see how TDataframe solves this.
So the framework gives you a couple of ways to pull data out depending on what you're doing. For general analysis on the CPU, sure, you can get a T-double matrix with high-precision 64-bit numbers. But for machine learning, the real prize is the T-device matrix. This represents data living directly in the GPUs on super-fast VRAM using the more efficient 32-bit format that GPUs are built for.
And this line of code from the demo, this is where the magic happens. Get batch as device matrix is the star of the show here. It takes a slice of your data frame, a batch of 128 rows in this case, and sends it directly to the GPU. There are no intermediate copies in system RAM. It's a direct point A to point B transfer.
And the performance is just staggering. The demo log shows that sending a batch of 128 rows to the GPU takes about half a millisecond. This is how you prevent your expensive GPU from just sitting around twiddling its thumbs waiting for data. You keep it fed, and this is how you do it efficiently.
Okay, so doing these steps one by one is cool, but for a real project, you need a clean, reusable pipeline. That's where some of the higher-level abstractions come in, which the demo shows off with things like the iData provider.
The iData provider is just a brilliant piece of design. You can think of it like a smart conveyor belt for your data. It wraps your data frame, and its one job is to serve up perfect little batches of data already separated into features and targets ready for your training loop. This keeps your data logic separate from your model logic, which is fantastic for writing clean code.
And that smart, efficient design just keeps on going. So you've got one big data provider and you need to split it for training and validation data, right? No problem. One command, split. And guess what? It's another zero-copy operation. It doesn't duplicate a single byte of your actual data. It just intelligently manages the indices.
So as we wrap up our little tour here, let's just step back and ask, why does all this matter? Why is this native, performance-first approach such a potential game changer for Delphi developers who want to get into data science?
Well, it all boils down to the Dataframe advantage. You get blistering native speed from multi-threaded Pascal. You get extreme memory efficiency, thanks to all those zero-copy operations. You get that direct, high-speed connection to the GPU that minimizes overhead. And maybe best of all, it's all wrapped up in an API that feels familiar because it plugs right into the T-dataset world you already know and love. All of this with zero external runtimes or dependencies to worry about.
So, I'll just leave you with this thought. In a world where everyone seems to be chasing the latest, greatest, and often slowest framework, could the biggest leap forward actually come from going back to what we've known all along as fastest? The raw, unmatched power of compiled, native code? It's definitely something to think about for your next data-heavy project.